So we have learned about primal problems and the dual problem of a primal problem. And today we will learn the relation between the computational relation between the primal and the dual problem. And also we will learn how to proceed with phase 2 in the simplex method when there is an artificial variable still in the basic variable, still as a basic variable. This case we have left it behind in chapter 2, and we said we will learn how to proceed with such a case in section 3.3, and here we are. Okay, so in this section we will use what we have learned in the previous two sections to modify our computations using the simplex method. So this is what it says. We now modify the form of the table. So the table we are using, we will modify the form. Then computations will become faster. Okay, how we do that? We will add an additional row and column. Okay, what is the additional row? The row is above the column labels and contains the vector. So we will add this as an additional row in the top of the table. And we will add this column here at the right of the table, this column here. But notice that, what do we mean by CI1, CI2, CIN? We are assuming that we have a basic variable, assuming the basic variables are denoted by the indices xi1, as we have learned before, xi2, all the way to xim. Okay, now what we do, we go to the cost vector here and we pick CI1, where it is. It might be C1 or C2 or C5, somewhere from here. And CI2, the same thing. We pick them all from here and make a vector that we put at the left of the table. Okay, to explain this, we must go through an example. So we will take the linear programming problem from section 2.3, as we see here. Okay, now this is the linear programming problem after converting it to a canonical form. So we have artificial variables here to be x 7, 6, and 8, right? These are the ones we introduced. Now we have actually x, if we go back to the original problem in example 2 of section 2.3, we will find that x6 was, let me write it here, x6 was a slack variable. Okay, and we have y1 and y2. We call this, actually in that example, y1, and we call this y2. But now we want to use the same notation, so we will call that artificial variables. Instead of y1, y2, we will say x7 and x8. So x7, x8 are artificial variables. Okay, now we see the matrix A. We know how we get it out from the system, and the resources vector B and the cost vector C. Remember the cost vector C, where it comes from. It is the coefficient of x's in the objective function Z. So it is 1, minus 2, minus 3, minus 1 here, minus 1, plus 2, and we may add plus 0x7 plus 0x8. That's why we have a 0 in here and 0 in here. Okay, remember all that? Good. Okay, now, because we have artificial variable, then we will make the auxiliary problem, okay, having the artificial variables as basic variables. Artificial and slack variables are basic variables. And then we start phase one and then do the bivoting. And at the end of phase one, we will get a table that we will use as a start to obtain a starting table for phase two. Remember that? Okay. And the idea of phase one is to get rid of the artificial variables, okay, as basic variable. We don't want them to be basic variables anymore. This is at the end of phase one. Remember all of that? Okay. Now, what we were saying here, adding the row. This is the row. Now the cost vector here. Now remember, for the auxiliary problem, okay, we have a cost vector. The cost vector for the auxiliary problem, how we get it? Remember, it is that the objective function of the auxiliary problem is minimize. Minimize what? Z prime equals y1, which is now x7 plus x8. x7 plus x8, which means, but to work the simplex method, we will convert it to a canonical form, and we will say we convert this to maximize z prime equals minus x7 plus, sorry, minus x8. Remember that? We convert the minimize to maximize, but we multiply the objective function with -1. Okay, so the cost function here now, the cost function with a transpose is given by 0, 0, 0, and 0. Two more zeros, -1, -1. Good. This is the cost function of the cost vector of the objective function of the auxiliary problem. Okay, and why we have it this way? Because this is a coefficient of x1, coefficient of x2, x3, all the way till coefficient of x6, and this is the coefficient of x7, and this is the coefficient of x8. Right? The coefficients of x1 to x6 are all zeros. Okay, now what we mean above there by adding one more row in the top to the table, we mean adding this row here. Good? Okay. Now, what do we mean by adding? What do you mean by adding this part of the cost vector that corresponds to what? To the basic variables. So what are the basic variables? The basic variables here are the slack and the artificial ones. So the basic variable, let me write here. We know that the basic variables are x6, x7, x8. This is for the auxiliary problem. We are working now in the auxiliary problem, okay? So what we will do, we will choose the coefficient of x6, 7, and 8, okay? That will give us what? CP transpose, which is our CP, let me just write it this way, which consists of 0 for x6, but pay attention to the order. X7 comes first in the first constraint. So we will go for the coefficient of x7, then x6 comes in the second constraint, so it is in the second coordinate, and x8 comes in the third constraint. Okay? And to make sure what I'm saying here, so this coefficient goes here, this one goes here, and this coefficient goes here. So these are the coefficient of the basic variables. And therefore, this is the vector CB. And we add it here. X7, X6, X8. We have to put them in that order because this is their order in the constraints. Okay? Okay. So what we have done here, we want to work a linear programming problem, but we find ourselves need to introduce a slack and artificial variables, and therefore, because we have artificial variables, we need to work with the auxiliary problem. And now at the beginning of the section, we said we will add the cost function on the top, and a part of the cost function that corresponds to the basic variables to the left, and they are highlighted in yellow and green. Now, what we do, we work simplex method. But now, because of these notations, the simplex method will be easier to work. Okay. Now, you remember how we get the matrix B? Now, the indices are I1 is 7 because this is x7. And because of x6, we get I2 is 6. And x2, we get I3 equals 2. Why are we doing so? Because we know that x8 will be leaving now. Okay, I missed something. We need to compute the, before I go down here, sorry, before I speak about this, we need to compute the entries in the objective row. We don't have it yet. Okay, and we know how to compute it, right? So remind me how to compute zj. How we compute zj? It equals cp transpose times tj minus cj, right? And what is cp transpose? We have it there. Okay, everything is there. What is tj? Tj is the column j, right? So to compute this in here, z1, this is z1, how we compute it. This is z2, how we compute that. So let's go. z1, this gives us the following. z1 equals CP transpose, it is -1, 0, -1. We have done such a thing before. T1, which is 1, 1, 3, minus C1, which is 0. This is C1, right? This is T1. This is C2, and so on. Compute this, what we get, -1 plus 3, it is 2, minus 0, it is 2. Good. Now help me please to compute the remainings. Z2 equals Now we will take it easy. To compute Z2, what I do, multiply -1 with 2. I could do the same thing for the first entry. Multiply 0 with 2, multiply -1 with 6, add them all and subtract from above C2. So I have -2, -6, -8 minus 0. So we get here -8. Okay. Now how I get the entry after that? I multiply -1 by 2, 0 by 1, -1 by 2, add them and subtract C3 from above there. So I get -2 and -2, -4. So in here I will have -4. I will continue doing so, doing such a thing. Okay, to obtain the third entry in the objective row, multiply -1 by this, multiply by that, and multiply by this. What we get? -2 in here, right? And now I think you can complete the remainings. We get -1 and -3, -4 again in here. Please correct me if I'm doing some mistake in the computations. And what I get 0 here. Now what I get in here, I get -1 minus -1, so I get 0. And in here I get -1 minus the -1 above there, so I get also 0. So again, this is C7, this is C8, and so on. Okay, now if you notice, it is much easier now to work with the simplex method, to work it this way. Huh? Use this column here, multiply it by the columns, add, subtract from the thing from above, and then we are done. Good. Now, what is the entering variable here and what is the departing variable? So we notice we have a -8 is the most -1, and compute, we will get apparently this is the bivoting, the bivote. So the entering variable is x2, and no, did I make some mistake? So the entering variable is x2 and the leaving variable is x8. Yes. Yes. So the entering variable is x2 and the leaving variable is x8. Good. So what we are doing now is nothing new. Just introducing the row and the column. Now, x8 is the departing and x2 is the entering. And now we have this new basic variable. So I1 is 7, I2 is 6, now I3 is 2. Okay? So we need to fix, we need to fix this will be -4. Yes, thank you. This must be -4. Any other corrections? Sihan and Ines, thank you. Okay, good. Now we have new basic variables. What we do with these new basic variables, we use them to form the matrix B. Remember, the matrix B consists of the column of I1 and then the column of I2. Let me write them this way. Want the space to be appropriate. The column of I1 and then the column of I2 and then the column of I3. right? But I1, I2, I3, they are, this is the column, the 7th column, and this is I2 is the 6th column, and I3 is the 2nd column, correct? So we will go and take I7, we will go and take I7, put it here, okay? In that order, remember the order, and then I6, put it here, and then I2, put it here. Good? Good. And therefore, we obtain B inverse. What do we need B inverse for? Now, remember that to compute the new table, the columns of the new table, we will use what? Tj equals, who tells me? Do you remember that? How I use B to compute Tj? Actually, let me write it here. Tj equals, who tells me? I want to compute the columns of the new table using the columns of the initial table, of the previous table. So how we do that? B inverse Aj. Okay, for some reason I want to go back and write it here. Tj, yeah, thank you, Siham, is B inverse Aj, simply. So now, if we substitute here, so we will not do computations. But if I take this column in here, substitute it here, then I get this column. Agree? Again, if I take this column, substitute it here, then I obtain this column. And so on for all columns, right? So we have done such computation before. Okay, good. Now, the objective function, the above row is still as the same as the first one. But notice here that we have changed the CP, the cost row. Why? Because here we are choosing, let me write here, because of that now, because of this, CB equals what? CB equals C7, C6, C2, right? And we go back to the cost function we have for the auxiliary problem, or working with the auxiliary problem. So this is -1, 0, and 0. And that's why we have it here. Good? Okay. Now, we will compute the entries in the objective row in the very similar way. So for example, so again here, Zj equals, what was that? CB transpose Tj minus Cj, which is simply, if I want to compute this, I multiply, for example, this by this by that, and this by this. What I get? -4/3. And then I subtract the 0 from here, then I get 4/3. Now again, if I want to obtain this, see how I obtain that? I multiply this with -1 all the way, with -1, multiply this with 0, multiply that with 1/6, then what I get? -1/3 times -1, it is 1/3 minus the -1 above here, which means +1. So 1 over 3 plus 1, then I get 4 over 3. Okay? How I get the negative 4? I multiply this column, negative 1, 0, 0 by 4, 10, 4, and then add. All right? I get negative 4. Okay, which means how I get this negative 4? It was CP transpose times XP, right? Okay, how I get XP here from the above one? We did not mention it. How I obtain XP here? How I obtain 4, 10, 4 out of the previous table? What we do? Do you remember that? Somebody tells me, please. My question is how I compute that? How I computed this out of the previous table? Can somebody tell me? Huh? Anyone? How did I get 4, 10, 4? This is my question. So what did I multiply with what? P inverse times 12, 18, 24. Is that true? Then I get 4, 10, 4. Remember? To obtain a column from in the table below, we multiply the corresponding column above by B inverse. And same things applies for the very last column. Just multiply it by B inverse. And multiply that and make sure we got things correctly. Yes? Okay. Okay, good. Do you remember that now? Okay. Now we got the new table. Okay, how we computed the objective, the entries in the objective row, we have already done. Okay, now. Okay, so we got this table. So we will continue the simplex algorithm to form the table below. So one more step of the algorithm give us this. Okay, so actually x7 will be leaving, departing, and x3 will be entering. So do the computation the very same way. We reach this table. So gives an optimal solution to the auxiliary problem. So we are still working with the auxiliary problem. So we have an example. We had to make an auxiliary problem for it because we introduced artificial variables. And now we reached the final table of phase 1. Now what we do? We want to get rid of the artificial variables, right? Okay. So the next step is to form initial table for phase 2. Remember that now. Remember that the original objective function, now we bring it here. The original objective function is this. And therefore, C equals 1, negative 2, negative 3, negative 1, negative 1, 2. Right? Here it is. So again, in preparing the table for Phase 2, we will use the cost vector of the original objective function. Now, what are the basic variables that we ended with at the end of phase 1? They are x3, x6, and x2. So we will take the coefficient C3, this is, so C3, yes, and this is C6, and this is C2, right? Where are they? C2 is here, so I need some space. C2 is this, and we start with C3. C3 is this, and C6 is that. Okay, good. So we added the vector of the objective row. We added the vector of the basic variables. Okay, and what we do moving from phase 1 to phase 2, we take the table, or remove the columns of the artificial variables, and take everything as is. Now, how we computed these things here? Now, my question, how we computed -2, 0, 0, this, and that? How we computed them? Actually, we used again Zj equals Cb transpose Tj minus Cj. For example, Z1 equals Cb transpose is -3 to -2 times C1, which is 0, 0, 1 half, minus C1, which is 1. So what I'm doing here, just multiply this by this by that, this by this, then I get -1, right? Add them together. Minus 1 above there, so I get -2. And to obtain, for example, the column in here, I multiply -3 with this, -2 with that, and -2 with this. Then what I get? -3 over 2 plus 1, which is -1 half, minus the 1 half of above there, which is -1. So -1 half minus -1, so -1 half plus 1, which is 1 half in here. Okay, now you know how we got everything in here, and the 3 is obtained similarly. How this is obtained? This is obtained by just multiplying CB transpose by XB. Okay, good. So we formed the initial table of phase 2 now. Okay, now work by voting. You either do by voting as you learned by using row operations, or using the matrix B if you wish to use the matrix B here. So who tells me what is the matrix B if I want to use it? Like say for example, we want to compute that. Where B equals. Now who tells me, who gives me the first column of matrix B? So I'm waiting somebody to give me the first column of matrix B. 1, 0, 0. That is 4. Where we got this from? So let me see. This x3. Okay, good. 1, 0, 0. Yes, I will write 1, 0, 0 here. And then for x6, 0, 1, 0. Thank you, Siham. And then for x2, 0, 0, 1. Oh, okay, so it is the identity matrix. So this was for x3, 1, 0, 0. And then for x6, 0, 1, 0, and then 0, 0, 1. This is 0. Okay, good. Okay, now we use this metric to obtain the new table, do by voting, and then we get there. And then we are done. Good, thank you. and we have reached the optimal solution, right? So here we have reached an optimal solution to the original problem, which says x3 is what? x3 is 3, right? And what? So let us write them all. We start with x1. x1 is what? Okay, tell me please, x1 is what? x2 is what? So x1 is 0. Are you sure? x3 is what? x4 is what? And we want the original variable. We don't want to evaluate slack variable. Okay. So x1 actually is 6, right? Yes, 6. Thank you for correction. x2, 0, x3, 3, x4, x4, 0, x5, again 0, x6, 9. The value of the objective function is z equals what? 15. And how we compute that? We go back to the formula here. We just substitute these values. Okay, good. So شو اللي عملناه لحد الآن؟ احنا ما عملنا شيء جديد، احنا بس اللي عملناه هنا قدمنا the new row and the new column بس. ماشي الحال؟ يعني احنا اشتغلنا مثال كنا مشتغلينه من أول. So we done nothing new so far. Just only introducing the new row on the top and the new column at the left. We done nothing, right? Okay. So why did we do that? We did nothing new. So what this section is talking about? What is new about this section? Okay. اللي عملناه لحد الآن فقط عشان تتعود على هذه الحركة. New row, new column. بس. وتتعود على حساب كيف تحسب الانتريز. So what we have done so far is just to get you used to the new row and to the new column, and then multiply the column and get the entries in the objective rows, and obtaining the columns of the new table from the previous one using the matrix. We are getting used to this. So what the reason we introduced this example, we started with this example, is to get used to the new form of the table in the simplex method only. Okay, now we get used to it. Okay, we will see what new thing we will develop for this section. Now we start from here. So what new thing we will develop for this section? Okay, let us see. We have now defined enough tools to complete our discussion of artificial variable. Oh, okay, our discussion of artificial variable are not complete yet. The answer is yes. You remember the case where at the end of phase 1, an artificial variable, some artificial variables, still basic variables. Okay, so working simplex method with phase 1 and phase 2. At the end of phase 1, we have two cases. One case No artificial variable is the basic variable anymore, and then we know how to complete that from chapter 2. The other case is having some artificial variable still as basic variable, and we did not want know how to work it out to complete it. We will learn now. Now, if one of these artificial variables takes a positive value, then we are done. Because in such a situation, the linear programming problem has no solution. But we are now assuming, we will assume now, some artificial variable at the end of phase 1, some artificial variable, still basic variables, and have value 0. What we do? Now we will see what we do. Okay. Now, this is what we are saying. Recall that we have taken the problem in canonical form, as in here. Remember everything. With a B positive. And we introduced artificial variables. And we called them y1, y2, y3. And we took for the auxiliary problem this objective function. And we want to minimize it and make it 0 actually. Right? Okay. Now, suppose that at the end of phase 1, the minimum of this objective function is 0. That this is what we want, to have 0. But there are artificial variables which remain basic at value 0. Again, if some of them remain basic at value positive, then we are done. The linear programming problem has no solution. But some of them may stay at value 0. In the final optimal table, in the final table of phase 1. Then what we do? Okay, what we do is the following. Page 2, how we work it out. Okay, so the initial table for page 2 is the final table of page 1 with the following multiplication. So we take the final table of page 1. What we do? Delete the columns from the final table of base 1 that labeled with non-basic artificial variable. Okay, we know that. So some artificial variable are basic, and some of them are not basic anymore. Remove these, but remove the columns under this. But there is a basic variable, an artificial variable, which is still basic. Do not remove the column under it. Do not. Just remove the column of the artificial variable that are not basic anymore. Okay. Now, replace the row above the column in labels. This is the new row we added. Okay. With what? With the coefficient of the original objective function, assigning 0 as cost for each of the basic artificial variables. Good. احنا عملنا هذا قبل شويه في page 2. So go back to the original function, take the cost vector of it. But the original function does not have an artificial variable there. So what I put in the row in there, I put 0. Okay? In the place of the artificial, the coordinate of the artificial variable. Okay, good. Now form the vector CB from the new objective function coefficient. Okay, we know that. Now calculate the entries in this way. Good. The new procedure for selecting variables is as follows. Okay. Now we made the table using procedure steps A, B, C, D. Now we want to do the by voting. But in here, there's something different. How to select the departing variable. See that if at least one of the entries in the negative entries in the entering variable, we know how to decide the entering variable. Go to the least negative number in the objective row. We know how to do that. Okay. Now, once we do that, we get a column which is the column of the entering variable. This is what we are talking about. Now, at least one of the entries in the entering variable column corresponding to a row labeled by artificial variable is negative. If this is happening, choose one of these artificial variable as departing variable. Okay. Now what it says, we have chosen the entering variable. Okay. Now we look at the artificial variable. If we find that the entry in the row of this artificial variable and in the column of the entering variable, if the entry is negative, then we will choose this artificial variable to be the departing. Okay, so again, we have already the entering column. We go to artificial variable and choose the row of the artificial variable and see the entry in that row and in the entering column. If we find entry is negative, then that artificial variable will be kicked out. Okay? Now, if we find such a thing. Now, what if we don't find such a thing? What we do? There is an exercise which says that one of them, such a thing must happen. Such a thing must happen. Okay? For some reason. Okay? And this is an exercise number 18. Okay. Now let us apply everything here. Okay. In section 2.3, we showed that the problem given example 5 ended with an artificial variable in the basis. Will you work this example using the two-pace method? Okay. So this example in section 2.3, we stopped and we said we will do it in section 3.3, and here we are. So the problem in canonical form is given that way. Okay. Now for pace 1, we need to introduce these artificial variables. Good. And this is maximize. We must make it, sorry, minimize. We must make it maximize to work the simplex method and give it negative. Okay. Now the CP here is -1, -1, and -1. Good. And because the C is 0 for x1, 0 for x2, 0 for x3, -1, -1, -1. So this part here is CP transpose. Now this is the cost vector of the auxiliary problem. We are working in pace 1. Now we use all that information to form the table and give it the new form. Okay, here we go. Have fun now, do the work. Okay, and you know we got this table from this, provided us with this table. Okay, and how we obtained this, multiply this by that, -3, -8, -2, this is -13, -0. Good. Okay, and do the same for the rest. Okay, good. So we obtained the table for the starting table of base 1. Now do by voting. Then we get that. You know how to do all that work. Keep going and keep going. And then boom. This is the final table of base 1. So I will leave the computation for you to check out. This is the final table of base 1. Now we want to use it to make the initial table of base 2. Now what does it say? We go to the procedures above here and apply them all. Okay. Now it says delete the columns of the artificial variables that are not basic. Replace the row above the columns with the coefficient of the original objective function, and then form CP. Okay, so let's go. Now the artificial the basic variables here are x1, x3, and y1. Y1 is artificial variable, and it is basic variable. So now y2 and y3 and their columns, we can get rid of them because they are not basic anymore. But we have to keep the column of y1, and I need to be careful. I don't want to take the negative one above there because this will be replaced with the new row. Okay? Okay, good. Now, remember that the original function, objective function, was this above here. So let's copy it. This is the original objective function, right? So we will use it to make the new objective vector. So this gives us that C equals 1 for x1, 2 for x2, 1 for x3, and 0 for y1. This 0 goes for y1. And let me confirm that. And this goes this way. So good. This is the new objective row. And the objective column, sorry, the objective, this part, let me write it without transpose. I have some space in here. So we will take, this is x1, x1. So the order is x1, x2, x3, right? The order of the variables x1, x2, x3. So I will go for 1 here. This is here. X3, sorry. So I go for x3, and then I go for y1. And here we go. Okay, I should not write it this way. Okay, okay, boom. I will go back and write this is transpose. Okay, so this in here is that. Boom. Okay, so this is the idea. Now do by voting. Okay, as we have learned before, we apply the simplex method in selecting the departing variable. Now this is the idea. We make sure that the entry of the row labeled by y1 and the bivoted column is non-negative. So this is the bivoted column, right? And now the entry here is non-negative, so it stays. If it is negative, then we kick y1 out. But it is not negative. So if it is not, we will choose y1 as the departing variable, which means if it is not non-negative. Okay? If it is non-negative, it stays. If it is 0 or positive there, it stays. Okay? If it is not negative, it stays. But if it is negative, then y1 will go out if it is negative. So this means if the entry is negative, the not here means negative. Which entry? This entry we're talking about here. So the entry in the row labeled by y1, the row of y1, and the entering column. Okay. So do by voting. x3 is the departing variable, x2 is the entering variable. Then we reach that table, and then we reach the solution. So we did not kick y1 out. It insisted to stay basic variable, but at value 0. So it does not affect the value of the original objective function because it is not there. Okay. Solution to the dual problem from the Tableau of Primal problem. So once we have the tableau of the primal problem done using the simplex method, we can use it to obtain the solution of the dual problem. Remember the dual problem. Okay, so how is that going to be? So to introduce it, we will discuss first the easiest case. What we mean by the easiest case, where the problem, the primal problem, is in canonical form. Okay? Once we understand that, we will go and work it out in general for any primal problem, not necessarily the canonical form. But we need to understand this first. Okay. Now, there are two easy description of finding optimal solution dual problem. The dual problem is, okay, let's see. This is the dual problem as we learned before, right? But notice here, uh, W is unrestricted. Why W is unrestricted? Who tells me why the variables of the dual problem are unrestricted? Okay, good to see him again. W here is unrestricted because of this equality. Do you remember when moving to primal, from primal to dual? This causes W to be unrestricted. Okay, good. Now, remember we want to obtain a solution for this. This is our goal now. Okay, how we do it? Simply the solution is boom, here we go. This is the optimal solution, and we can obtain it by doing that. But what is B inverse? What is B? Let us see what is B. It here says where the matrix B consisting of certain columns of the initial table. Certain columns? Certain columns of the initial table? Which columns? Okay, let's see. The columns that are used in B correspond to the basic variables of the final table. I want you to pay attention to this, to the basic variable of the final table of the primal problem. Okay, pay attention to this. It says the columns are from the initial table. This sentence is kind of confusing. No, it says B, the columns of B are taken from the initial table. And then it says the columns that are used in B corresponds to what? Now again, the columns of B are from the initial table, but the question, which columns I take from the initial table? Now the second sentence says, correspond to the basic variable of the final table. Now we go to look at the final table. We will find the basic variables. You know, moving from a table to a table changes the set of basic variables every time we have entering and departing. At the end, final table, at the end, we will have a set of basic variables, right? We will look at them and go back to the initial table and take the columns under them. Got it? So from the final table, we will know what are the basic variable at the end. We will take the columns under them from the initial table. This is the matrix B. And then you compute B inverse. But now in this second sentence here, it helps you very much. It tells you how to obtain B inverse without even having B. Oh, this is good, interesting. So how that happens? Okay, the column in the final table with the same labels as the initial basic variables and arranged in the same order. So this is هذا العكس. This is the opposite. It says we will take the columns from the final table. But which columns? That has the same labels as the initial basic variables. Oh, okay. Now, B, for B, we will go to the final table, take the basic variable, know the basic variables, and take the common from the initial table. For B inverse, we do the opposite. We look at the initial table and see what were the basic variables there, and we will know what they are, right? So put them in hand. Now do the work till you get the final table. Now in the final table, look at the top row and find out the basic variables in hand here. They are this, and that, and take the columns from the final table, but under the initial basic variables. This is easier, much easier to obtain B inverse. Okay, so obtaining this matrix B, well, and using CBT, we get W, which is a solution for the do. Oh, this is easy. So let's do an example. Well, good. This is an example. Consider as our primary problem the near programming problem. So this is our problem, the near programming problem. This one here. Okay. Now we want to know a solution for the dual problem. So this is the dual problem, and it says minimize, as you know. This is the dual problem, right? Okay. Okay. And you know how to find it. So we want to find a solution for it. Okay. So we will go to the primary problem and work it out. But we need to make it as canonical form. So we need to introduce a slack variable here. There is no need for artificial variables. So these are the slack variables. Okay. Now make the initial table. Now the initial table, and it has basic variables, this one, and this one, x4, x5, and x6. Okay. Okay. Now the matrix B are the columns under these, the columns and the column under what sphere? Under 4, sorry, yes, x4 and x5, and x5, and no, sorry, what is the matrix B here? Where we got solving this problem by using the simplex method. Okay, B here is what? B here is what? Sorry. This is the column under x4, 136, x2, and then x1, x4, x2, and x1. That's because of okay. No, I shall not try this here for now, because uh, these are okay. So no, sorry. Let it be here for a while. Just forget it now. Now do the by voting from here to here. Do the by voting from here to here. So I just told you how to obtain the matrix B. This is not the very same matrix B as we used to for, okay, before. هذه ليست نفس ماتريكس بي اللي استعملناها بالاول. ماتريكس بي هاي اللي تكلمت عنها هنا راحت عن بالي. So matrix B, we will to find the matrix B لازم نشوف ما يلي. اولا نروح على الفاينل تيبل، اوكي، ونشوف سوري نعم، نروح على الفاينل تيبل وناخذ مين البيسك فاريبلز اللي ظهروا هناك، x4 x2 x1، فبناخذهم نفس الترتيب x4 x2 x1. سو هذا للx4 هي هنا، x2 x1. So هذه هي الايديا. Go to the final table and see the basic variables. Get them from there. Go back to the initial table to this basic variable in the top and take the columns you get to be. Now, how we get B inverse? Getting B inverse is the opposite. Now, getting B inverse goes the opposite way. Go to the what? To the initial table, take the basic variable x4, x5, x6. This is from the initial table. These are basic variable. And then go to the columns under them, but from the final table. If you do that, you get the inverse. This is much easier. So we want the one in orange. Then we get the inverse. And now, as we learn here, this one here, we can compute W transpose. Okay? And here W transpose is CB transpose, which is 098. What is ZB? CB is the very last column here, the column, the CB of the very last table. Multiply them and then we're done. So this is easy. How to get solution of the primal problem from the tables, the initial and the final table of the primal problem. But so far we have discussed the canonical form, the case of the canonical form of the primal problem. What if the primal problem is not in the canonical form? What we do, we will see now. Good. Now let us consider how to find the solution of finding the solution of the dual problem of an arbitrary general linear problem, not necessarily in the canonical form. Okay, as we discussed before, okay, maybe the original problem is given this way. In here, it means some constraints are inequalities less than or equal. Some other constraint, a group of constraints is inequalities greater than or equal, and some other constraints are equalities. And in here, B is B2 is positive. Okay. Now working the dual problem of this. Now A parentheses 1 means the first set of constraints that are less than or equal. Just we put them together and make a matrix for them. So A parentheses 1 means the matrix of that part. And B parentheses 1 means the resources vector of that part, and so on. Okay? Now, make the dual problem. So this is the dual problem. Why do we have negative here? Okay? Because to make the dual problem, we need to have less than or equal. So we will multiply this. We will make that this way. Negative A2x is less than or equal negative B2. And that's why we have the negative here. Okay? Now pay attention why W3 is unrestricted. This is because somebody have already answered this question previously. This is because we have equality here. And remember this table says whenever we have equality, whenever the ith constraint is equality in the primal, then the ith variable is unrestricted. Okay? Now we want to find, we seek a solution to 4 using 3 from the final table of 3. This is 3 here. So we want to find the solution of the primal problem using the final table of problem in 3. Okay? How we do that in general? Okay, this is the explanation. If the two-base method is used, the columns labeled by artificial variable must not be discarded. This one, must not be discarded. In this case, so again, the artificial variables must not be discarded. must not. لازم نخليهم. if we have to use the two pace method معناه انه عندنا artificial variables. So at pace 1, at the end of pace 1, you get a table and keep the artificial variable there. Don't kick them out. Okay, why? They must be kept throughout pace 2. Okay. And must be modified accordingly by each by voting step. Therefore, you keep these columns and work with them by voting. Consider them as any other ordinary column. However, okay, however what? However, the entries in the objective row labeled by this artificial variable must not be used when checking optimality. So we are keeping the columns of artificial variables, but the entries in the objective rows, they might be negative. That's fine. The optimality criterion says what? You keep by voting from table to table till the entries in the objective row are all non-negative, are all non-negative. But now it says, don't worry about the entries in the objective row below the columns of the artificial variables. If some of them are negative, that's fine. Do not consider any negativity here in these columns. Do not consider them when you apply the optimality criterion. So we may say, okay, we have reached optimal solution, but still some negative values in the column of the artificial variable exist, and that is fine. Okay. Now this means there are maybe negative numbers in the objective row when an optimal solution is reached. This is what I have just said. But these numbers will only be in the columns labeled by artificial variables. That's fine. This is what I have already said. Okay, now P inverse, as we have done already, P inverse will be automatically a variable as described in the final table مثل ما شرحنا. وعندها هذا solution. ليش بنسميها؟ لأنه maybe when we multiplied by negative 1 here, when we multiplied by negative 1 here, that causes the following. When we reach the solution, we will go back to the variables. Which variables? Go back here. We multiplied some constraints with negative 1, right? And constraints in the primal problem corresponds to variables in the dual problem. Now, once we reach the solution, we will go to this variable and multiply them by negative 1 again, so that we change nothing. Okay? This is the difference between what we have just done in case 1 and in this case. Now, this will be clear using this example. Now, consider our primary problem in the linear programming. Okay, so this is our primary problem. And then see here, after multiplying the second constraint of the primary problem by negative 1. So we must replace this. We must replace this by negative 2x2 plus x3 less than or equal negative 5. When you replace it, then get the dual problem after you do so, right? And that's actually why you have negative 5 in here, because of this. We don't have 15, 5, 10 as we used to. No, we will replace the 5 with negative 5. Okay? Good. So this is the dual problem, and pay attention that W3 is unrestricted, and the reason is this equality. Huh? Okay. Remember the table above there, which is very important, and there are exercises to work because we are using this table a lot of times. Okay. Go to exercises of section 3.1, which makes you get used and more handy uh, with that table. Okay, now we want to find a solution for the dual problem at the left. Okay, so we will go and make the initial table and the final table of the primal problem. But we have to introduce artificial variables. Okay, so we got auxiliary problem. So we got that. So we got the initial table. This is the initial table of the base 1 of the auxiliary problem. And the basic variables are x4, y1, and y2. Okay. Now do the by voting from here to here. At the end of base 1, we have that. Okay. Now we want to go to page 2. But now what we said, do not delete the columns of the artificial variable. Keep them there. And by vote them, that's fine. And keep working the simplex method. So here we go. Now, this is at the end of page 1. We get this table. Now, convert it to page 2. Huh? And you know how to make that. Now, this is the page 2. We start with this table. Now, do by voting. Do by voting, and then we reach the final table. Okay. Now we go on to get the B inverse. The B inverse says what? You go to the basic variables at the beginning, x4, y1, y2, and take the columns under them in the final table. Did we say what? x4. So we will take this. y1, we will take that with this. And y2, we will take that. And here we go. This is B inverse. This is B inverse. And just to distinguish things. And this is what? CB. Multiply, we get the solution of the dual problem. Congratulations. And the dual problem is here. I copy it here again. Okay. Now, notice that, go back. This is what I wanted to explain. Go back. What we have done to this constraint, we multiplied it by -1. It is the second constraint. So we will go to the second variable of the dual problem, the solution, and multiply it by negative. So this is W hat. This is why we're saying hat, W hat, because this is not our final solution. Because some of the entries must be multiplied by negative, and it is W2. And once we do that, then we reach the solution we are looking for, which is, what shall I give it, which color? This color. And this is the solution. Good. Now, remember from the last section we said, when the primal problem has an optimal solution, then the dual has optimal solution. And now, the value of the objective function of the dual at this solution is the same, is equal to the value of the objective function of the primal at the solution of the primal. They give you the same value of objective function. Now, is that true? This is W1, W2, W3. Substitute them in the objective value of the original of the dual problem. Where's the objective value of the dual problem? It is here. 15W1 minus 5W2 plus 10W3. And here we go, we get this number. Okay, now that table, the final table, from this final table here, we get the solutions. X1, X2, X3. Substitute them in the in what? the objective function of the original problem. In here, 3x1 plus 2x2 plus 5x3. We said 3x1 plus 2x2 plus 5x3. 3x1 plus 2x2 plus 5x3. This is all multiplications, and must give us the same value, which is the same as that one. Good. And we are done with this section. Anyone has any question, please go ahead.